Year. Let's see. Am I live? Am I live? I am live. Let me make my mic a little bit louder. And do you not hear anything? What if I play? Property. No. Alright, let's see. My mic. Property. No. Alright, let's see. My mic. So desktop audio can be a little bit louder. Like that. Let's see if that works with my mic and the music at the same time. Pause. So desktop audio can be a little bit louder. Like that. Let's see if that works with my mic and the music at the same time. Pause. Alright, I can make my mic a little bit louder. Let's see. And the music at the same time. Pause. Alright, I can make my mic a little bit louder. Let's see. Alright, I can make my mic a little bit louder. Let's see. Alright, so now talking with the music. See if this works. If it does, I'll keep it. Let's go. Alright, so now talking with the music. See if this works. If it does, I'll keep it. Let's go. Alright, so now talking with the music. Awesome. See the live chat there. Awesome. I don't want to learn more. Alright, whatever. So I want to put that there. Put that there. If I do this. Put that here. Whoa. Where do I want? I want face. Oh shit! I want face this way. So I'm gonna do that. Do this. And then, how do I change the title? Spelled around. Okay. Yeah, I'll say it's education. I'll say it's not made for kids. I don't care. And then for my OBS, I want to switch to Window 2. And that will be this. Khan Academy.
We left off, we were trying our very best to get to the castle and save whomever we were needing. We left off, we were trying our very best to get to the castle and save whomever we were needing. We left off, we were trying our very best to get to the castle and save whomever we were needing.
All right, let's get this going.
To save. But we had to cross the bridge, and the troll gave us these clues because we had no money in our pocket. And if we don't solve his riddle, he's going to push us into the water. So we are under pressure. And at least we made some headway in the last video. We were able to represent his clues mathematically as a system of equations. What I want to do in this video is think about whether we can solve for this system of equations. And you will see that there are many ways of solving a system of equations. But this time I want to do it visually, because at least in my mind, it helps really kind of get the intuition of what these things are saying. So let's draw some axes over here.
Before I do that one, no, not Code Academy, Code Wars. I was looking at my thing earlier and I couldn't do shit. Let's see, basic operator value 1, value 2. Your task is to create a function that does 4 basic mathematical operations. Operation string slash character, value 1, value 2. Return a result of numbers after applying the chosen operation. So add, subtract. How am I gonna do this? Return value 1 plus value 2. Evaluator equals minus. Pretty sure it's an easier way of doing this. Return value 1 minus value 2. Aleph operator. I'm spelling it wrong. Operator. The equals what's next? Multiplication. Return value 1 times value 2. Else return value 1 divided by boom. Submit. Boom! I wasn't able to do that 4 months ago. Or you could just do all ifs. That's cool. Evaluate. Boom, bitch. Alright, this one I might have some trouble with. And minus 1. It's not scriptable. 3, 4, 8, 5, 9, 7. This doesn't work because I don't have n in there. Can I be creative? For I and n. I'm lost. I know there's something really easy. Something like this. Return. I just forgot how to write it. Do I write in? No, it's not like that, yeah. I've been doing math lately. Yeah, this. Int x for x and string n. There we go, you see. We get a reverse. That's cool. Let's do another one. My coding is a little rusty now because I've been doing some math. 1, 2, 2 should return 9 because 1 squared plus 2 squared plus 2 squared equals 9. This is the easy one. Why did this not return a value? But this that's interesting. So for I numbers, I know this is not right. Oh, I don't know why I'm doing that. I squared. Squared I? Uh, Local variable total reference before assignment. What the fuck does that mean? See if I have something similar. Oh, not easy. I Oh, that's why. 2. What does this mean? What does that mean? Let's figure that out. Python. Should be outside. Hmm, that doesn't work. Turn. What was it? Some. And not iterable. X2 for x in numbers. I squared for I in numbers. Did I do some? Ah, that's why. So for every, so it's gonna go for. So for I in numbers, 1, it's gonna do 1 squared, which is 1. Next one, 2 squared, which is 2. Add the sum. My coding skills is weak right now. They were better like a week ago. But I have to do math, so.
Let's draw an f-axis. That's the number of 5s that I have. And let's draw a t-axis. That is the number of 10s I have. And let's say that this right over here is 500 10s. That is 1,000 10s. And let's say that this is, sorry, that's 500 5s. That's 1,000 5s. This is 500 10s, and this is 1,000 10s. So let's think about all of the combinations of f's and t's that satisfy this first equation. If we have no 10s, then we're going to have 900 5s. So if we have no 10s, we're going to have 900 5s. So that looks like it's right about there. So that's the point. 0 10s, 900 5s. But what if it went the other way? If we have no 5s, we're going to have 900 10s. So that's going to be the point. 900 10s, 0 5s. So all the combinations of f's and t's that satisfy this are going to be on this line, are going to be on that line right over there. And I just draw a dotted line just because it's easier for me to draw it straight. So that represents all the f's and t's that satisfy the first constraint. Obviously, there's a bunch of them, so we don't know which is the one that is actually what the troll has. But lucky for us, we have a second constraint, this one right over here. So let's do the same thing. In this constraint, what happens if we have no tens? If tens are 0, then we have 5f is equal to 5500. Let me do a little table here because this is a little bit more involved. It's a little bit more involved. So for the second equation, tens and fives. If I have no tens, I have 5f is equal to 5500. F will be 1100. I must have 1100 fives. If I have no,
It's too loud.
we left off, we were trying our very best to get to the castle and save whomever we were needing over there. And I just draw a dotted line just because it's easier for me to draw it straight.
No. Okay. Ooh.
Fives, if I have no fives, and this is 0, and I have 10t is equal to 5500, that means I have 550 tens. So let's plot both of this point. T equals 0,
What
f
the
is
fuck?
1100.
I just missed it. So if f is 0, 5500 divided by 10, 550. Okay, there we go. And then 550 divided by 5. So T0. Okay.
It's right about there. So that is 0, 1100 is on the line that represents this equation. And that when f is 0, t is 550. So let's see, this is about, this would be 6, 7, 8, 9. So 550 is going to be right over here. So that is the point. 550, comma 0. And all of these points, let me try to draw a straight line again. I can do a better job than that. So all of these points are the points. Let me try one more time. We want to get this right. We don't want to get pushed into the water by the troll. So there you go. That looks pretty good. So every point on this blue line represents an FT combination that satisfies the second constraint. So what is an f and t, or number of fives and number of tens, that satisfy both constraints? Well, it would be a point that is sitting on both of the lines. And what is a point that is sitting on both of the lines? Well, that's where they intersect. This point right over here is clearly on the blue line, and it is clearly on the yellow line. And what we can do is, if we drew this graph really precisely, we could see how many fives that is and how many tens that is. And if you look at it very precisely, and actually I encourage you to graph it very precisely and come up with how many fives and how many tens that is. Well, when we do it right over here, I'm going to eyeball it. If we look at it right over here, it looks like we have about 700 fives, and it looks like we have about 200 tens. And this is based on my really rough graph, but let's see if that worked. 700 plus 200, 700 plus 200 is equal to 900. And if I have 700 fives, 700, let me write this down. 5 times 700 is going to be the value of the fives, which is $3,500. And then 10 plus 10 times 200, 10 times 200, which is $2,000. $2,000 is the value of the tens, and if you add up the two values, you indeed get to $5,500. So this looks right, and so we can tell the troll, I know how many $5 and $10 bills you have. You have 700 $5 bills, and you have 200 $10 bills. The troll is impressed, and he lets you cross the bridge to be the hero or heroine of this fantasy adventure.
What if you don't want to draw a graph?
Is negative 1 comma 7 a solution for the system of linear equations below? And they give us the first equation is x plus 2y is equal to 13. Second equation is 3x minus y is equal to negative 11. In order for negative 1 comma 7 to be a solution for the system, it needs to satisfy both equations. Or another way of thinking about it, x equals 7 and x is equal to
Yeah, I was about
negative
to
1.
say.
This is the x coordinate. X equals negative 1 and y is equal to 7 need to satisfy both of these equations in order for it to be a solution. So let's try it out. Let's try it out with the first equation. So we have x plus 2y is equal to 13. So if we're thinking about that, we're testing to see if when x is equal to negative 1 and y is equal to 7, will x plus 2y equal 13? So we have negative
Oh
1
yeah.
plus 2
Negative
times
1 plus
7,
14
y
equals
should be
13.
7. This needs to be equal to 13. And I'll
Uh-huh.
put a question mark there because we don't know whether it does. So this is the same thing
Okay,
as
3
negative 1
minus.
plus 2 times 7 plus 14. That does indeed equal
No,
13. This is
and
negative 1 plus 14. This is 13. So 13 does
not the
does
second equation.
definitely equal
10 does not
13. So
negative 10 does not
this
equal negative
point,
11.
it does at least satisfy this first equation. This point does sit on the graph of this first equation, or on the line of this first equation. Now let's look at the second equation. I'll do that one in blue. We have 3 times negative 1. 3 times negative 1 minus y, so minus 7, needs to be equal to negative 11. And I'll put a question mark here because we don't know whether it's true or not. So let's see. We have 3 times negative 1 is negative 3. And then we have minus 7 needs to be equal to negative 11. I'll put the question mark there. Negative 3 minus 7, that's negative 10. So we get negative 10 equaling negative 11. No! Negative 10 does not equal a negative 11. So the x equaling negative 1 and y equaling 7 does not satisfy this second equation. So it does not sit on its graph. So this over here is not a solution for the system. So the answer is no. It satisfies the first equation, but it doesn't satisfy the second. In order to be a solution for the system, it has to satisfy both equations.
Cool.
Just in case we encounter any more trolls who want us to figure out what types of money they have in their pockets, we have devised an exercise for you to practice with. And this is to solve systems of equations visually. So they say right over here, graph this system of equations and solve. And they give us two equations, this first one in blue, y is equal to 7/5 x minus 5, and then this one in green, y is equal to 3/5 x minus 1. So let's graph each of these, and we'll do it in the corresponding color. So first, let's graph this first
The
equation.
blue one
So
is
the first thing I
none.
see is that its
The
y-intercept
y-axis
is
is
negative
-5.
5. Or another way to think about it, when x is equal to 0,
And do
y is going to be negative
rise
5.
7 over
So let's
5.
try this out. So when x is equal to 0, y is going to be equal to negative 5. So that makes sense. And then we see its slope is 7/5. This was conveniently placed in slope-intercept form for us. So it's rise over run. So for every time it moves 5 to the right, it's going to move 7 up. So if it moves 1, 2, 3, 4, 5 to the right, it's going to move 7 up. 1, 2, 3, 4, 5, 6, 7. So it'll get right over there. Another way you could have done it is you could have just tested out some values. You could have said, oh, when x is equal to 0, y is equal to negative 5. When x is equal to 5, 7/5 times 5 is 7, minus 5 is 2. So I think we've properly graphed this top one. Let's try this bottom one right over here. So we have when x is equal to 0, y is equal to negative 1. So when x is equal to 0, y is equal to negative 1. And the slope is 3/5. So if we move over 5 to the right,
They intersect.
we will move up 3. So we will go right over there. And it looks like they intersect right at that point, right at the point x is equal to 5, y is equal to 2. So we'll type in x is equal to 5, y is equal to 2. And you could even verify by substituting those values into both equations to show that it does satisfy both constraints. So let's check our answer. And it worked.
Awesome.
The following two equations form a linear system, all right? This is one equation. It has x and y, so it's going to define a line. And then I have another equation that involves x and y, so it's going to define another line. It says graph the system of equations and find its solution. So we're going to try to find it visually. So let's graph this first one. And to graph this line, I have the little graphing tool here. Notice if I can figure out 2 points, I can move those points around, and it's going to define our line for us. So I'm going to pick 2 x values and figure out the corresponding y values, and then graph the line. So let's see how I could do this. So let's see. An easy one is what happens when x is equal to 0. Well, if x is equal to 0, everything I just shaded goes away, and we're left with negative 3y is equal to 9. So negative 3y equals 9, y would be negative 3. So when x is equal to 0, y would be negative 3. So let me graph that. When x is equal to 0, x is 0, y is negative 3. Now another easy point, actually, instead of trying another x value, let's think about when y is equal to 0, because these equations are written in standard form, so it's easy to just test, well, what are the x and y intercepts? So when y is equal to 0, this term goes away, and you have negative x is equal to 9, or x would be equal to negative 9. So when y is 0, x is negative 9. So when y is 0, x is negative 9. Or when x is negative 9, y is 0. So I've just plotted this first equation. So now let's do the second one. We'll do the same thing. What happens when x is equal to 0? When x is equal to 0, so this is going to be our y-intercept now. When x is equal to 0, negative 6y is equal to negative 6. Well, y would have to be equal to 1. So when x is 0, y is equal to 1. So when x is 0, y is equal to 1. Get one more point here. When y is 0, when this term is
negative 1,
y
0.
being 0 would make this entire term 0, then 6x is equal to negative 6, or x is equal to negative 1. So when y is 0, x is negative 1, or when x is negative 1, y is 0. When x is negative 1, y is 0. And so just like that, I've plotted the 2 lines. And the solution to the system are the x and y values that satisfy both equations. And if they satisfy both equations, that means they sit on both lines. And so in order to be on both lines, they're going to be at the point of intersection. And I see this point of intersection right over here. It looks pretty clear that this is the point x is equal to negative 3 and y is equal to negative 2. So it's the point negative 3 comma negative 2. So let me write that down. Negative 3 comma negative 2. And then I could check my answer. Got it right. Let's do another one of these, maybe of a different type. So over here it says a system of 2 linear equations is graphed below. Approximate the solution of the system. All right, so here I just have to look at this carefully and think about where this point is. So let's think about first its x value. So its x value, let's see, it's about right there in terms of its x value. It looks like,
Negative
so
1
this is
-1/2.
negative 1, this is negative 2, so negative 1.5 is going to be right over here. It's a little bit to the left of negative 1.5, so it's even more negative. I would say negative 1.6. So when I'm approximating it, negative 1.6, hopefully it has a little leeway in how it checks the answer. What about the y value? So if I look at the y value here, it looks like it's a
1.2.
little less than 1.5.
1.3.
1.5 would be halfway between 1 and 2. It looks like it's a little less than halfway between 1 and 2. So I don't know, I'd give it 1.4, positive 1.4. And let's check the answer, see how we're doing. Yep, we got it right. Let's actually just do one more for good measure. So this is another system. They've just written the equations in more of our slope-intercept form. So let's see, y is equal to negative 7x plus 3. When x is equal to 0, we have our y-intercept. Y is equal to 3. So when x is equal to 0, y is equal to 3. And then we see that our slope is negative 7. When you increase x by 1, you decrease y by 7. So when you increase x by 1, you decrease y by 1, 2, 3, 4, 5, 6, and 7. When x goes from 0 to 1, y went from 3 to negative 4. It went down by 7. So that's that first one. Now the second one, our y-intercept, when x is equal to 0, y is negative 3. So let me graph that. When x is 0, y is equal to negative 3. And then its slope is negative 1. When x increases by 1, y decreases by 1. So the slope here is negative 1. So when x increases by 1, y decreases by 1. And there you have it. You have your point of intersection. You have the x-y pair that satisfies both equations. That is the point of intersection. It's going to sit on both lines. That's the point of intersection.
1, negative
And that's
4.
the point x equals 1. In this video, we're going to get some more practice setting up systems.
All right, let's do some math now. 2 times 1 plus 2 equals 4. So 2 times 2 is 2 plus 2 is 4. Yes, the first one. Yes. Next one, x and y. So 2 equals 3 times 1 minus 1. 3. 3 minus 1 is 2. Yes. There's no x value on this one. Let me do this one. 7 times 5 plus 6 times 1 equals 7. Yeah, I can't really tell. It's going to be a nope. No. So you plugged 1 in for y. 5 does equal negative 5. So you just skip x. Okay. Yeah, this. Okay. Minus 2 plus 4 times 3 equals negative 9. 4, 8, 12 plus negative 2 negative 10. Or 10. No. Let's do the bottom one. 7 equals 3 times 3 minus 2. 9 minus 2 is 7. 7 equals 4, 8, 12, negative 12, 5. Yes. The answer is what? Negative 12 minus 5. No, the answer is no. I almost forgot my negative. That would have been bad. Let's go, baby. Negative 5. Negative 5. And negative 2 over 1. So it's going to be boom. Negative 2. And it's going to be positive. Oh, 1, 2, 1. X equals That's gonna be -1. Oh no, -1. So it's less than negative. So it's gonna be one of these two, and y is 3. Less about 3.5. Haha. Y equals mx plus b. So y is gonna be 4, -4. X is just 1. So it's gonna be doot, doot. Y is 2. And x is 4. So it's gonna be 1, 2, 3, 4. Boom. They intercept at -2, -6. 2, So these is not in slope intersect form. Should I make it in slope intersect form? Yeah, why not? -3x y equals 18 plus 3x plus 3x -9y equals 3x plus 18. Divide everything by -9, -9, -9. Y equals -1 over 3x minus 2. I don't like that. No, 1/3. Actually, it doesn't matter. -2. And it's gonna go 1, 2, 3, 1. This one is 4x plus 3y equals 12 minus 4x 3y equals -4x plus 12 divided by 3 divided by 3 divided by 3. 4. So it's going to be 4 -4 3. So it's going to be 1 2 3 1 2 3 4. The answer is 6 -4. My girlfriend takes me. I'll respond later. Yeah, flip it around. Same thing. Gotta switch it to slope intercept form. Get 3x plus 3y equals 9 plus 3x. So it's going to be 3y equals 3x plus 9 divided by 3 divided by 3 divided by 3. Y equals x plus 3. Other one, actually, I'm going to do a 3. And then x is 1. So the slope is 1, so it's going to be 2, 2. And then the next one, 2x minus 7y equals -14 minus 2x negative 7y equals 15. Divide everything by -7. Y equals 2 over 7x plus 2. 2. Ooh, 2 over 7. So it's going to be 1, 2, 3, 4, 5, 6, 7. 1, 2. So it intercepts at x is -1.5 to -1 2/5 to y is 1, 1.5, 1 3/5. Proficient. Thank you very much. Right.
Up systems of equations, not solving them, but just setting them up. So we're told Sanjay's dog weighs 5 times as much as his cat. His dog is also 20 kilograms heavier than his cat. Let C be the cat's weight and let D be the dog's weight. So pause this video and see if you can set up a system of equation, two linear equations with two unknowns that we could use to solve for C and D, but we don't have to in this video.
So you said 2? Sanjay's dog weighs 5 times as much. D equals 5 times C. Just
All right, so let's do it together. So what I like to do is usually there's a sentence or two that describes each of the equations we want to set up. So this first one tells us Sanjay's dog weighs 5 times as much as his cat. So how much does his dog weigh? So his dog weighs D. So we know D is going to be equal to 5 times as much as his cat weighs. So his cat weighs C. So D is going to be equal to 5 times as much as his cat weighs. So that's one linear equation using D and C. And so what's another one? Well, then we are told his dog is also 20 kilograms heavier than his cat. So we could say that the dog is going to be the dog's weight is going to be equal to the cat's weight plus what? Plus 20 kilograms. We're assuming everything's in kilograms, so I don't have to write the units. But there you have it. I have just set up two equations in two unknowns, two linear equations, based on the information given in this word problem, which we could then solve, and I encourage you to do so if you're curious. But sometimes the difficult part is just to re-express the information that you're given in a mathematical form. But as you see, as you get practice, it becomes somewhat intuitive. That what we see in blue is just another way of writing what we underline in blue, and what we see in yellow is just another way of writing or expressing what we underlined in yellow up there.
how many do I have left? 2 more.
In this video, we're going to get a little bit of practice setting up systems of linear equations based on a word problem. We're not actually going to end up solving it. You can do that if you like, just for kicks. But really, we're going to just focus on setting it up. So here we're told Lauren uses a blend of dark roast beans and light roast beans to make coffee at her cafe. She needs 80 kilograms of beans in total for her next order. Dark roast beans cost $3 per kilogram. Light roast beans cost $2 per kilogram. And she wants to spend $220 total. Let D be the number of kilograms of dark roast beans she buys, and L be the number of kilograms of light roast beans she buys. All right, so based on this information,
Let me set it up before he talks about it. Lauren uses a blend of dark roast beans and light roast beans to make coffee at her cafe. She needs 80 kilograms of beans in total Damn. Dark roast beans cost $3 per kilogram. Light roast beans cost $2 per kilogram. So it'll be huh. 3 times D plus 2 times L equals 220.
Information that we've been given. See if you can pause this video and set up a
I
system of
already did it,
equations that's
bitch.
going to have two equations with two unknowns, D and L, that in theory we could solve to figure out the right number of kilograms of dark roast beans and light roast beans that Karen should use. So pause this video and try to work that out. All right, now let's do it together. And what I'm going to do is
I'm gonna send a quick text to someone. Actually, I'll shoot an email. Email sent.
I'm going to underline, so let's see. We know that D is dark roast beans and L is the number of kilograms of light roast beans. And then they tell us here, they say she needs 80 kilograms of beans in total. So what we could say is, hey, the number of kilograms of dark roast beans plus the number of kilograms of light roast beans needs to be equal to 80 kilograms. So the number of kilograms of dark roast beans plus the number of kilograms of light roast beans, I'm having trouble saying light roast beans. Well, this, what I just underlined here, it says needs to be 80 kilograms in total. So that needs to be 80. So this number of kilograms plus this number of kilograms is going to be equal to your total number of kilograms. All right, so I have one equation with two unknowns. Let's see if we can get another one. So next, they say dark roast beans cost $3 per kilogram. Light roast beans cost $2 per kilogram. And she wants to spend $220 total. So what I just underlined in this aquamarine color, we can set up another equation with. And if you haven't already set up your system of equations, see if you can now do that. See if you can set up the second equation. Pause the video. All right, well, the way to think about it is we just have to have an expression for how much does she spend on dark roast beans, how much does she spend on light roast beans, and then we need to add those two together, and that needs to be equal to $220 because that's how much she wants to spend in total. So how much does she spend on dark roast beans? Well, it's going to be the number of kilograms of dark roast beans that she buys, and it says that it costs $3 per kilogram. So we're going to multiply it by 3. $3 per kilogram times the number of kilograms of dark roast beans. This is how much she spends on dark roast beans. And so how much is she going to spend on light roast beans? Well, she buys L kilograms of light roast beans. They told us that there. And they cost $2 per kilogram. So $2 per kilogram times the number of kilograms. This is how much she spends on light roast beans. So you add how much she spends on dark roast to how much she spends on light roast. And so this is going to be $220 in total. And there you have it. We have our two equations with two unknowns. And so now we could go and solve it, but you can do that outside of this video. But the whole point of this video is to understand how to construct these based on the constraints, based on the information that we see in this. So typically, when you're trying to set these up, there's often a sentence or two that will focus on one equation. So this first one is saying, hey, the kilograms, let's add those up for the total number of kilograms. And then there's another sentence or two that'll focus on, in this case, some other equation. In this case, it's the price. So the price of the dark plus the price of the light is going to be equal to the total amount she wants to spend. In this video, we're going to get those to understand how to construct these. We're told that Lauren uses a blend of dark roast beans and light roast beans to make coffee at her cafe. She needs 80 kilograms of beans in total for her next order. Dark roast beans cost $3 per kilogram. Light roast beans cost $2 per kilogram, and she wants to spend $220 in total. Then they tell us here's a graph that shows a system of equations for this scenario where X is the number of kilograms of dark roast beans she buys, and Y is the number of kilograms of light roast beans she buys. All right, let me scroll down so we can take a look at this. And so sure enough, so this blue line, and I'll write it out in blue, this X is the number of kilograms of dark roast beans, Y is the number of kilograms of light roast beans, and she wants to buy a total of 80 kilograms. That's what they told us up here. We can go back to look at that she needs, I'll underline this in blue, she needs 80 kilograms of beans. So that constraint, that the sum of the kilograms of dark and light is equal to 80, that's represented by this equation. And if we were to graph it, that is this blue line right over here. And then this other constraint, 3x, well, the dark roast beans cost $3 per kilogram. So 3x is how much she spends on dark roast. 2y is how much she spends on light roast, because it's $2 per kilogram. And 220 is the amount that she spends in total. And they tell us that up here. Dark roast beans cost $3 per kilogram. Light roast beans cost $2 per kilogram. And she wants to spend $220. So this equation is another way of expressing what I just underlined up here in green. And the green line shows all of the XY combinations that would match these constraints. And so now let's do something interesting. They've labeled some points here, points C, D, F, and E. And we're going to think about what do each of these points represent. So for example, this point C that is on the green line, but it sits above the blue line. What does this tell us? What does this point C represent? Pause this video and think about it. Well, if we're on the green line, that means that the amount that she spends on dark roast plus the amount that she spends on light roast is adding up to exactly $220. So she's definitely spending $220 at C. But how many total kilograms is she using? Well, the fact that for this given x, we're sitting above the line, that means that she is not using exactly 80 kilograms. And we can see that over here. She's using, looks like 10 kilograms of dark, and it looks like something like 95 kilograms of light. If you were to add those 2 points together, it looks like she's using something closer to 105 kilograms. So point C is a situation where she is spending exactly $220, but she's using more than 80 kilograms because it's not meeting this second constraint. It's sitting above that line. Mm-hmm. Now let's think about point D. What does that represent? Pause the video and try to figure that out. Well, because we sit on the blue line, that means that we are meeting this constraint, that the kilograms of dark and light combined is equal to 80 kilograms. So she's using exactly 80 kilograms here. But what about her spending? Well, because this point lies below the green line, that tells us that we are spending less than $220. And we could even try it out. 3 times 20 plus 2 times 60 is what? 60 plus 120 is $180. And so this is a point where we're meeting this constraint, but we're not meeting this constraint. We're underspending right over here. Now, what about point F? Well, point F sits below both of these lines. So pause your video and think about what that means. Well, if we're sitting below both of these lines, that means that neither are we spending $220, nor are we using 80 kilograms. And you could see that if you actually look at the numbers. You don't have to do this, but this is just to make you feel good about it. It looks like she is using 30 kilograms of dark and 30 kilograms of light. So in total, she is using, so this is a situation where she's using 60 kilograms in total, not 80. And so that's why we're not sitting on this blue line. And if you look at how much she's spending, she has 30 kilograms of each. So 3 times 30 plus 2 times 30, that's going to be 90 plus 60. That's also less than 220. And so that's why we see this point is below these lines. And then last but not least, what does point E represent? Well, point E sits on both of these lines. So that means that it meets both of these constraints. This is a situation where she is spending exactly $220 and the total number of kilograms she's using of dark and light is exactly 80. And so if we wanted to say, hey, what combination of dark and light would she need in order to meet both constraints?
But yeah. Ilya rode her bicycle from her house to the beach at constant speed. Let's do per hour. And then she rode from the beach to the park at constant speed per hour. Total duration of the ride. Yeah, yeah. Let B be the number of hours it took Ilya to ride from her house to the beach. Okay. So B the number of hours from her house to the beach. Let me redo it. 18 km per hour. And then rode from the beach to the park. Hmm. The total duration of the rides was 1 hour, and the distance she rode in each direction are equal. Does it make sense? Oh, so she was going slower, so she went less distance. Wait, so the distance, the distance is 10 miles. 10 miles. Since she's going faster. I'm confused. Okay, so B equals, no, P plus B equals 1. So it's these two. I gotta see how. How is this equal though? So let's say they're so from point A to point B. This one shows going 18. This one shows going 15. Oh, okay, so this was 1 mile. This one was 1 mile. Since she was going faster, she probably did in like 20 minutes. And this one, since she was going slower, she probably did in 40 minutes. Okay. Why was I able to write? Next question. Lindsay's 5 years younger than Mark. 7 years ago, the sum of their age was 31. Let L be Lindsay's age and M be Mark's age. So you do M minus L Mark So Lindsay's age equals Mark plus 5. Nope. Lindsay's age equals Mark minus 5. Yes. This answer. And then you do Lindsay minus 7 plus Mark minus 7 equals 31. Yep. Avery uses a blend of dark chocolate and milk chocolate to make ice cream topping at a restaurant. She wants to buy 10 kilograms more of dark chocolate than milk chocolate. She needs 150 kilograms of chocolate in total for her next order. Let D be the number of kilograms of dark chocolate he buys and the number of kilograms of milk chocolate. Okay, so you do D plus 10 Let's just go step by step. So, dark chocolate equals milk chocolate plus 10. Yes. Milk chocolate, nope. dark chocolate equals 10. No. Milk chocolate equals dark chocolate plus 10. Nope. This one. Dark chocolate equals, so you milk chocolate plus 10. Then 150 kilograms of chocolate enter next total. So then you do D plus. Chevy has some yarn that she wants to use to make hats and scarves. Each hat uses 0.2 kilograms. H be the number of hats Chevy makes, and S be the number of scarves. So each hat uses 0.02 of kilograms of yarn. So hats times 0.2 plus scarves S times 0.1. Chevy wants to use 2 kilograms of yarn to make a total of 15 items. So so you do H plus S equals 2. So H plus S equals 2. So it's A and C. And then a hat uses H 0.02. What? Oh, this one. So H and S is kilograms of yarn, so that equals 2. Then you do 0.2 and 0.1 times. You do 1. Does it make sense? 1 times 0.2 is 0.2 plus. What? Each hat uses 0.2 kilograms of yarn. H is hats. What the fuck? Why was it? Piece of shit. I wasn't done reading it. right back. It's making me redo this. Alright, let's see if I can do it real quick. And the entire work 2 hours and this issue was let B, so I remember it's B plus 2. So B plus B is 2. Kevin is 3 years older than Daniel. 2 years ago, Kevin was 4 times as old as Daniel. Kevin is 3 years older than Daniel, so you do K equals Daniel plus 3. She's by 120 chocolate and tofu next to what a recipe calls twice the amount of dark chocolate as milk chocolate. Dark chocolate equals 2 times M. Yep. Each high uses so has 2. No! No! I didn't really get this question. Oh, I know why. It's because I was in the middle of fucking reading the hints. There we go. Okay. That's good enough. Oh, shit, I forgot. Casper has some whipping cream, 18% butterfat, and some milk. That's So 18, 4, 12. Oh, I can't draw on that. Okay. Mixture has less than the intended volume and more than the intended percent. This one. I represents where Chana is behind Josiah. My son uses a blend of white corn and yellow corn to make tortilla chips at a restaurant. She needs to buy 50 kilograms of corn in total for her next order of white corn. Well, that's how much she wants to spend, and this is how much she needs to buy 50 grams. Nope, nope. Uh, that wasn't a quiz, right? Okay. B times 8 P times 7. Total distance Toby skated was 20 kilometers. And it took him twice as long to get to the park. From the beach to the park took him twice as long. This is right, P equals 2B. Yep. So P equals 2 times B. Alright, let's see, is this a solution? So it's negative 8 plus 4 times 3 4. Yes, it does equal 4. Negative 8 plus 3 times 3 equals 1. So 3 times 3 is 9 plus negative 8 does equal 1. Yes. What does K represent on this quantity? I know what K, make sure it has a 10 volume. Make sure it's already in the form, so Y is 7. X is negative 2, so 1, 2, 1, 2. No, it's gonna go down Y, 1, 2, or 1. And then this one's gonna be negative 7. It's gonna go up 1, 2, 3, 4, 5. The point is X is 2, Y is, fuck, did I mess this up? 1, 2, 1, 1, 3. China. Yay! Yay, yay, yay! Holy shit, this is a lot of stuff. Gotta do it.
Just as you were solving the potato chip conundrum in the last video, the king's favorite magical bird comes flying along and starts
What potato chips in the last video?
whispering into the king's ear. And this makes you a little bit self-conscious, a little bit insecure. So you tell the king, what is the bird talking about? And the king says, well, the bird says that he thinks that there's another way to do the problem. And you're not used to taking advice from birds. And so being a little bit defensive, you say, well, if the bird thinks he knows so much, let him do this problem. And so the bird whispers a little bit more in the king's ear and says, okay, well, I'll have to do the writing because the bird does not have any hands, or at least can't manipulate chalk. And so the bird continues to whisper in the king's ear, and the king translates and says, well, the bird says, let's use one of these equations to solve for a variable. So let's use this blue equation right over here to solve for a variable. And that's essentially going to be a constraint of one variable in terms of another. So let's see if we can do that. So here, if we want to solve for m, we could subtract 400w from both sides, and we would have 100m is, if we subtract 400w from the left, this 400w goes away. If we subtract 400w from the right, we have is equal to negative 400w plus 1100. So what got us from here to here is just subtracting 400w from both sides. And then if we want to solve for m, we just divide both sides by 100. So we just divide all of the terms by 100, and then we get m.
Negative 4w.
We get m
plus
is
11.
equal to negative 400 divided by 100 is negative 4w. 1100 divided by 100 is 11 plus 11. So now we've constrained m in terms of w. This is what the bird is saying, using the king as his translator. Why don't we take this constraint and substitute it back for m in the first equation, and then we will have one equation with one unknown. And so the king starts to write at the bird's direction, 200, 200. So he's looking at that first equation now. He says 200, 200, and instead of putting an m there, the bird says, well, m, by the second constraint, m is equal to negative 4w plus 11. So instead of writing an m, we substitute the value for m. We substitute for m the expression negative 4w plus 11. So negative 4w plus 11, and then we have the rest of it, plus 300w. Plus 300w is equal to 1200. So just to be clear, everywhere we saw an m, we replaced it with this right over here in that first equation. So the first thing, you start to scratch your head and you say, is this a legitimate thing to do? Will I get the same answer as I got when I solved the same problem with elimination? And I want you to sit and think about that for a second. But then the bird starts whispering in the king's ear, and the king just progresses to just work through the algebra. This is one equation with one unknown now. So the first step would be to distribute the 200. So 200 times negative 4w is negative 800w. 200 times 11 is 2200 plus 2200. And then we have the plus 300w. Plus 300w is equal to positive 1200. Now we just need to solve for w. We first might want to group this negative 800w with this 300w. Negative 800 of something plus 300 of something is going to be negative 500w. And then we still have this plus 2200. Plus 2200 is equal to 1200. Now to solve for w, we'd want to subtract 2200 from both sides. So subtract 2200, subtract 2200. On the left-hand side, you're left just with the negative 500w, negative 500w. And on the right-hand side, you are left with negative 1000. And this is starting to look interesting. Because if we divide both sides by negative 500, we get w is equal to 2, which is the exact same answer that we got when we tried to figure out how many bags of chips each woman would eat on average. When we tried to solve it with elimination, we got the exact right answer. So at least for this example, it seems like the substitution method that this bird came up with worked just as well as the elimination method that you had originally done the first time you wanted to figure out the potato chip conundrum. And if now you actually wanted to figure out how many chips the men would eat, well, you could do exactly the same thing you did last time. You know one of the variables, you can substitute it back into one of the equations and then solve for m. And you can try that yourself to verify that you actually will get the same value for m as well. And in fact, this would probably be the easiest equation to substitute into because it explicitly solves for m already.
Just making sure I didn't skip. There's no elimination. Okay.
So that it's less likely that we get shown up by talking birds in the future, we've set up a little bit of exercise for solving systems of equations with substitution. And so this is the first exercise, or the first problem they give us. Negative 3x minus 4y is equal to negative 2. Y is equal to 2x minus 5. So let me get out my little scratch pad, and let me rewrite the problem. So this is negative 3x minus 4y is equal to negative 2. And then they tell us y. Y is equal to 2x minus 5. So what's neat about this is that they've already solved the second equation. They've already made it explicitly solved for y, which makes it very easy to substitute for. We could take this constraint, the constraint on y in terms of x, and substitute it for y in this first blue equation and then solve for x. So let's try it out. So this first blue equation would then become negative 3x minus 4, but instead of putting a y there, the second constraint tells us that y needs to be equal to 2x minus 5. So it's 4 times 2x minus 5, 2x minus 5, and all of that is going to be equal to negative 2. So now we get just one equation with one unknown, and now we just have to solve for x. So let's see if we can do that. So it is negative 3x, and then this part right over here, we have a negative 4. I want to be careful right over here. We have a negative 4 that we want to distribute. We're going to multiply negative 4 times 2x, which is negative 8x. And then negative 4 times negative 5 is positive 20. And that's going to equal negative 2. And now we can combine all of the x terms. So negative 3x minus 8x, that's going to be negative 11x.
It's negative 2.
Negative 11x. And then we have plus 20. Plus 20 is equal to negative 2. Now to solve for x, we'll subtract 20 from both sides to get rid of the 20 on the left-hand side. Subtract 20 from both sides. On the left-hand side, we're just left with the negative 11x. Negative 11x. And then on the right-hand side, we are left with negative 22. Negative 22. Now we can divide both sides by negative 11. Negative 11. And we are left with x is equal to 22 divided by 11 is 2, and the negatives cancel out. X is equal to 2.
Am I still streaming?
So that represents all the f's and t's that satisfy the first constraint. Obviously,
Why does it want me creating a YouTube channel? Was I not live this whole time? I think I was. Yeah.
and so we're not quite done yet. We've done, I guess you could say, the hard part. We've solved for x, but now we have to solve for y. And we could take this x value into either one of these equations and solve for y. But this second one has already explicitly solved for y, so let's use that one. So it says y is equal to 2 times, and instead of x, we now know that the x value that where these two intersect, you could view it that way, is going to be equal to 2. So 2 times 2 minus 5. Let's figure out the corresponding y value. Minus 5. Minus 5. And so you get y is equal to, and that's where the home stretch, y is equal to 2 times 2 is 4 minus 5. So y is equal to negative 1. And you can verify that it'll work in this top equation. If y is equal to -1 and x is equal to 2, this top equation becomes -3 times 2, which is -6, minus 4 times -1, which would be +4. And -6 plus
substitute x, get y, and then now you substitute y for x, and you get, there we go. Practice problems. So x is already solved for, so -5 times 2y minus 15 plus 4y equals 3. So it's going to be -10y minus, is it 60? 15 times 5, 75. -5 times -15 plus 75. So now I'm just gonna, so this is gonna equal -6y equals -72. Yep, 72 divided by -6. Y equals divided by 12. Pulls it at 12. So y equals 12. And put that, and put y in the x formula. So x equals 2 times 12 minus 15. 24 minus 15 is 9. X equals 9. Y solve for 5 times -x plus 2 minus 7y equals 5x plus 10 minus 7. Wait, what? I'm stupid. Put it for x. I don't know what x is. 5x minus 7 times. So it's 5x minus -7 times. There's going to be plus 7x minus 14 equals 58. 8, 9, 10, 11, 12x minus 14. 8 plus 14 plus 14 x equals 6. Since I know what x equals, -6 plus 2, y equals 4. Bitch.
So now we have a very, very, very interesting problem.
Okay, hold up before I do that. Oh. Alright. all the system of equations we already have x, so 6 times y plus 3 minus 5y equals 15. So 6y plus 18 minus 5y equals 15 minus 18. So this equals y equals -3. So y equals -3. So that means -3 plus 3 is 0. X equals 0. What? How? This is preposterous. How did I get this wrong? X, so 6 times y plus 3. So I got 6y, 18 minus 5y equals 15. So that equals y and 18 minus 15, -3. What the fuck? Yeah, -3. 0, yeah. Did I not put the negative? Fuck. I always forget that. Y equals 7x. So I have a y. So 5x plus 2 times 7x. 5x plus 14x equals 9. 9x equals 9 divided by 9 divided by 9. X equals 1. 1, 1. And then y equals 7. So I have x now. So -10 times y minus 4 plus 3y equals 5. 10y minus 40 plus 3y equals 5. So this can equal -7y, which that equals 2. 45 divided by -7 divided by -7. Ay, ay, ay. I think I might have done this wrong. X equals -10 times -4. Haha, I knew I did it wrong. Huh. Equals positive. Who the fuck? Positive. So then I subtract 40. -40 minus 5. -40 plus 5 is -35. So y equals 5. So that means y equals 5. 5 minus 4 is 1. So we have y now. So it's 12x. X equals 0. Four. Booyah, I got all right, but I forgot the negative. The negative.
On the left-hand side of the scale,
How far am I? Almost halfway done. It's 6 o'clock right now. If I can get this done and then this done, I'll be sitting pretty. Oh, so pretty. Oh, so pretty. Systems of equations. So this one's a long one. This next one's short, and then this one's a long one, and then a decent one, and then a short, and then a short, and then a decent, and a decent, and then quadratic functions and equations into parabolas. What the fuck? Oh, so pretty. Oh, so pretty. Oh, so pretty. So pretty. Damn, so many text messages. Come on, come on, come on, come on. Shoot. Fuck. Okay, I'm done. I got sidetracked. Okay.
Left-hand side of the scale, I have two different types of unknown masses. One are these x masses, and we know that they have the same identical mass, and we'll call that identical, each of them have a mass of x. But then we have this blue thing, and that has a mass of y, which isn't necessarily going to be the same as a mass of x. But when I have two of these x's and a y, it seems like their total mass, or it definitely is the case, that their total mass balances out these 8 kilograms right over here. Each of these are 1 kilogram blocks. It balances them out. So the first question I'm going to ask you is, can you express this mathematically? Can you express what we're seeing here, the fact that this total mass balances out with this total mass? Can you express that mathematically? Well, let's just think about our total mass on this side. We have two masses of mass x, so those two are going to total at 2x.
Plus 1.
And then you have a mass of y. So then you're going to have another y. So the total mass on the left-hand side, and let me write it a little bit closer to the center, just so it doesn't get too spread out. On the left-hand side, I have 2x plus a mass of y. That's the total mass. The total mass on the left-hand side is 2x plus y. The total mass on the right-hand side is just 8. 1, 2, 3, 4, 5, 6, 7, 8. It is equal to 8. And since we see that the scale is balanced, this total mass must be equal to this total mass, so we can write an equal sign there. Now my question to you, is there anything we can do, just based on the information that we have here, to solve for either the mass x or for the mass y? Is there anything that we can do?
Yeah.
Well, the simple answer is, just with this information here, there is actually very little. You might say, well, let me take a y from both sides. You might take this y block up. But if you take this y block up, you have to take away y from this side, and you don't know what y is. And if you think about it algebraically, you might get rid of the y here, subtracting y, but then you're gonna have to subtract y from this side too. So you're not going to get rid of the y. Same thing with the x's. You actually don't have enough information. Y depends on what x is, and x depends on what y is. Lucky for us, however, we do have some more of these blocks laying around. And what we do is we take one of these x blocks and I stick it over here. And I also take one of the y blocks and I stick them over here. And I stick it right over there. And then I keep adding of these ones until I balance this thing out. So I keep adding these ones. So obviously if I just place this, this will go down, and because there's nothing on that side. But I keep adding these blocks. I keep adding these blocks until it all balances out. Until it all balances out. And I find that my scale balances once I have 5 kilograms on the right-hand side. So once again, let me ask you this information, that now having an x and a y on the left-hand side and a 5 kilograms on the right-hand side, and that fact that they're balanced, how can we represent that mathematically? Well, our total mass on the left-hand side is x plus y, x plus y, and our total mass on the, let me write that once again a little bit closer to the center. It is x plus y on the left-hand side. And then on the right-hand side, I have 5 kilograms. I have 5 kilograms. I have 5 kilograms on the right-hand side. And we know this is what actually balanced the scale. So these total masses must be equal to each other. And this information by itself, once again, there's nothing I can do with it. I don't know what x and y are. I can, if y is 4, maybe x is 1. Maybe x is 4, y is 1. Who knows what these are? The interesting thing is, we can actually use both of this information to figure out what x and y actually is. And I'll give you a few seconds to think about how we can approach this situation. Well, think about it this way. We know that x plus y is equal to 5. So if we were to get rid of an x and a y on this side, on the left-hand side of the equation, what would we have to get rid of on the right-hand side of the or if we get rid of an x and a y on the left-hand side of the scale, what would we have to get rid of the right-hand side of the scale to take away the same mass? Well, if we take away an x and a y on the left-hand side, we know that an x plus a y is 5 kilograms. So we would just have to take 5 kilograms from the right-hand side. So let's think about what that would do. Well, then I would just have an x left over here, and I would just have some of these masses left over there, and I would know what x is. And let's think about how we can represent that algebraically. Essentially, if we're taking an x and a y from the left-hand side, if I'm taking an x and a y from the left-hand side, I'm subtracting an x, I'm subtracting an x, and I am subtracting, actually, let me think of it this way. I am subtracting an x, I am subtracting an x plus y. I'm subtracting an x and a y from the left-hand side. But then what am I going to have to do on the right-hand side? Well, an x and a y we know has a mass of 5. So we can subtract 5 from the right-hand side. And the only way I'm able to do this is because of the information that we got from the second scale. And so I can take away 5. So this is going to be equal to taking away 5. Taking away an x and a y is the same thing as taking away 5. And we know that because an x and a y is equal to 5 kilograms. And so if we take away an x and a y on the left-hand side, what are we left with? Well, this is going to be the same thing. Let me rewrite this part. This taking away an x and a y is the same thing if you distribute the negative sign as taking away an x, and taking away a y, and taking away a y. And so on the left-hand side, we are left with just 2x, and we take away one of the x's. We're left with just an x. And we had a y, and we took away one of the y's, so we're left with no y's left. And we see that here visually. We have just an x here. And what do we have on the right-hand side? We had 8, and we knew that an x and a y is equal to 5, so we took away 5, and so to keep the scale balanced. And so 8 minus 5 is going to be 3. 8 minus 5 is equal to 3. And just like that, using this extra information, we were able to figure out that the mass of x is equal to 3. Now, one final question. We were able to figure out what the mass of x is, but can you now figure out what the mass of y is? Well, we can go back to either one of these scales, but it'll probably be simpler to go back to this one. We know that the mass of x plus the mass of y is equal to 5. So you could say, so one thing we know that x is now equal to 3. We know that this is now a 3 kilogram mass. We can rewrite this as 3 plus y. 3 plus y is equal to 5. Well, now we say, well, we could take 3 away from both sides. If I take 3 away from the left-hand side, I just have to take 3 away from the right-hand side to keep my scale balanced. And I'll be left with that the mass of y is balanced with a mass of 2, or y is equal to 2. That's analogous to taking 3 from both sides of this equation. And on the left-hand side, I'm just left with a y. And on the right-hand side, I am just left with a 2. So x is equal to 3 kilograms and y is equal to 2 kilograms. And what I encourage you to do is verify that it made sense right up here. Figure out what the total mass on the left hand and the right hand, or verify what the total mass right over here really was 8 to begin with. And you see that 2 x's are going to be 6 kilograms. Plus my y is 2 kilograms. That will balance 8 kilograms. And 3 plus 2 was equal to 5. Vivek and Kamala's teacher gave them a system of linear equations to solve. They each took a few steps that led to the systems shown in the table below. So we have the teacher's original system, what Vivek got after doing some operations, what Kamala got after doing some operations. Which of them obtained a system that is equivalent to the teacher's system? So the first question we should ask ourselves is what does it mean to even have an equivalent system? For the sake of this question, or for our purposes, an equivalent system is a system that has the same solution. So if there's some xy pair that satisfies the teacher's system, that is the solution to the teacher's system, well, Vivek's system, we're going to call it equivalent if it has the same solution. Similarly, if Camila's system has the same solution, then we're going to call it equivalent to the teacher's system. So let's make some comparisons here. So first, let's look at Vivek. So his first equation is actually unchanged from the teacher's equation. So any solution that meets both of these equations is for sure going to meet this top equation, because it's literally the same as the top equation of the teacher, so that works out. Now let's look at the second one. The second one is definitely, the second equation is definitely a different equation over here. We can check that it's not just being multiplied by some number on both sides. To go from 1 to 0, if you were multiplying, you'd have to multiply 1 times 0. And then if you wanted, in order to maintain the equality, you would have to do that on both sides. But 0 times this left-hand side would have been 0. You would have gotten 0 equals 0. So he didn't just scale both sides by some number. Looks like he did another operation. He probably looks like he's adding or subtracting something to both sides. So let's see how he could have gotten this right over here. So he took negative 4x plus 5y is equal to 1. And it looks like from that, he was able to get negative 3x plus 7y is equal to 0. So let's see what he had to do that. Let's see. He would have had to go from negative 4x to negative 3x, he would have had to add an x. So I could just write an x right over there. To go from 5y to 7y, he would have had to add 2y. So on the left-hand side, he would have had to add x plus 2y. Notice we have an x plus 2y right over there. And on the right-hand side, he would have had to add or subtract a 1 or add a negative 1. Notice we see a negative 1 right over there. So what he essentially did is he added the left-hand sides of these two equations to get this new left-hand side right over here, and he added the right-hand sides to get this new right-hand side. And that is a legitimate operation. This new equation that you got, this new linear equation, it's going to represent a different line than this one right over here, but the resulting system is going to have the same solution. Why do we feel confident that the resulting system is going to have the same solution? Well, for an xy pair that satisfies both of these equations, that's what a solution would be. For that xy pair, x plus 2y is equal to negative 1. So for that solution, we're adding the same thing to both sides. We're saying, look, I'm going to add x plus 2y to the left-hand side. Well, I need to add, if I don't want to change the solution, I have to add the same thing to the right-hand side. Well, they're telling us for the solution to this equation, x plus 2y is equal to negative 1. So negative 1 is the same thing as x plus 2y for that solution. So we're not going to change the resulting solution of the system. So it's a completely legitimate operation. What Vivek did is adding the left-hand sides and adding the right-hand sides to get this new second equation. That's not going to change the solution of the system. In fact, that's a technique we often use to eventually find the solution of a system. So now let's look at Camilla. So
That's weird.
her first equation is actually the exact same equation as the teacher's second equation. Now let's see, her second equation, how does it relate possibly to the first equation? So just looking at it offhand, it looks like she just multiplied both sides times a number. And it looks like that number, she clearly multiplied the right-hand side times negative 8. So times negative 8. Negative 1 times negative 8 is positive 8. And it looks like she also multiplied the left-hand side by negative 8. Negative 8 times x is negative 8x. Negative 8 times 2y is negative 16y. So she just multiplied both sides by the same value, which actually doesn't change the equation. This actually is going to be, it changes it the way it looks, but it actually represents the same line. So this is definitely still an equivalent system. You're going to these are still the same constraints. You're going to have the same solution. Whenever you're dealing with systems, you're not going to change the solution of the system as long as you either multiply both sides of an equation by a scalar, or you're adding and subtracting the equations. When I say add or subtract the equations, you're adding the left-hand side to the left-hand side, adding the right-hand side to the right-hand side like we had here, or subtracting the one from the other on the left-hand side, and we subtract the bottom from the top on the left hand, and we subtract the bottom from the top on the right hand, it's not going to change our solution. So both of them obtained a system that is equivalent, meaning that it has the same solution as the teacher's system. Scarlett and Hansel's teacher gave them a system of linear equations to solve. They each took a few steps that lead to the systems shown in the table below. So this is the teacher system. This is what Scarlett got after taking some steps. This is what Hansel got. Which of them obtained a system that is equivalent to the teacher's system? And just to remind ourselves, an equivalent system is a system that has, or at least for our purposes, is a system that has the same solution or the same solution set. So if there's a certain xy that satisfies this system, in order for Scarlett's system to be for it to be equivalent, it needs to have the same solution. So let's look at this. So Scarlett, let's see if we can match these up. So her second equation here, so this is interesting. Her second equation, 14x minus 7y is equal to 2. Over here, the teacher has an equation, 14x minus 7y is equal to 7. So this is interesting because the ratio between x and y is the same, but then your constant term, the constant term is going to be different. And I would make the claim that this alone tells you that Scarlett's system is not equivalent to the teacher. And you're saying, well, how can I say that? Well, these two equations, if you were to write them into slope-intercept form, you would see, because the ratio between x and y, the x and y terms, is the same, you're going to have the same slope, but you're going to have different y-intercepts. In fact, we can actually solve for that. So this equation right over here, we can write it as, if we subtract 14x from both sides, you get negative 7y minus 14, negative 7y is equal to negative 14x plus 7. And we could divide both sides by negative 7. You get y is equal to 2x minus 1. So that's this. All I did is algebraically manipulate this. This is this line, and I could even try to graph it. So let's do that. So I'll draw a quick coordinate. This is just going to be very rough. Quick coordinate axis right over there. And then this line would look something like this. So its y-intercept is -1, and it has a slope of 2. So let me draw a line with a slope of 2. Might look something like that. So that's this line right over here, or this one right over there. And let's see, this one over here is going to be, if we do the same algebra, we're going to have -7y is equal to -14x plus 2, or y is equal to, I'm just dividing everything by -7, 2x minus 2/7. So this is going to look something like this. Its y-intercept is -2/7. So it's like right over there. So this line is going to look something like, I'm going to draw my best attempt at drawing it. It's going to look something, actually that's not quite right. It's going to look something like, I'll just start right over here. It's going to look something like this. It's going to have the same slope, and obviously it goes in this direction as well. Actually, let me just draw that. So it's going to have the same slope, but a different y-intercepts. And that doesn't look right, but you get the idea. These two lines are parallel. So these two lines are parallel. So any coordinate that satisfies this one is not going to satisfy this one. They have no points in common. They are parallel. That's the definition of parallel. Since this and this have no points in common, there's no way that some solution set that satisfies this would satisfy this, because any xy that satisfies this can't satisfy this, or vice versa. They're parallel. There are no points. These two things will never intersect. So Scarlet does not have an equivalent system. Now what about Hansel? Well, we see Hansel has the same thing going on here. 5x minus y, 5x minus y, but then the constant term is different. -6, +3. So this and this also represent parallel lines. Any xy pair that satisfies this, there's no way that it's going to satisfy this. These two lines don't intersect. They are parallel. So Hansen's system is not equivalent either. In a previous video, we talked about the notion of equivalence with equations. And equivalence is just this notion that there's different ways of writing what are equivalent statements in algebra. And I could give some simple examples. I could say 2x equals 10, or I could say x equals 5. These are equivalent equations. Why are they? Because an x satisfies one of them if and only if it satisfies the other. And you can verify that in both cases, x equals 5 is the only x that satisfies both. Another set of equivalent equations, you could have 2x is equal to 8 and x equals 4. These two are equivalent equations. An x satisfies one if and only if it satisfies the other. In this video, we're going to extend our knowledge of equivalence to thinking about equivalent systems. And really, in your past, when you were solving systems of equations, you were doing operations assuming equivalence, but you might not have just been thinking about it that way. So let's give ourselves a system. So let's say this system tells us that there's some xy pair where 2 times that x plus that y is equal to 8, and that x plus that y is equal to 5. Now, we can have an equivalent system if we replace either of these equations with an equivalent version. So for example, many of you, when you look to try to solve this, you might say, well, if this was a -2x here, maybe I could eventually add the left side. And we'll talk about why that is an equivalence preserving operation. But in order to get a -2 out here, you'd have to multiply this entire equation times -2. And so if you did that, if you multiplied both sides of this times -2, what you're going to get is -2x minus 2y is equal to -10. This equation and this equation are equivalent. Why? Because any xy pair that satisfies one of them will satisfy the other. Or an xy pair satisfies one if and only if it satisfies the other. And so if I now think about the system where I've rewritten this second equation and my first equation is the same, this is an equivalent system to our first system. So any xy pair, if an xy pair satisfies one of these systems, it's going to satisfy the other, and vice versa. Now, the next interesting thing that you might realize, and if you were just trying to solve this, and this isn't an introductory video on solving systems, so I'm assuming some familiarity with it, you've probably seen solving by elimination, where you say, okay, look, if I can somehow add these, the left side to the left side and the right side to the right side, these x's will, quote, cancel out, and then I'll just be left with y's. And we've done this before. You can kind of think you're trying to solve for y. But in this video, I want to think about why you end up with an equivalent system if you were to do that. And one way to think about it is, what I'm going to do to create an equivalent system here is I am going to keep my first equation, 2x plus y is equal to 8. But then I'm going to take my second equation and add the same thing to both sides. We know if you add or subtract the same thing to both sides of an equation, you get an equivalent equation. So I'm going to do that over here. But it's going to be a little bit interesting. So if you had negative 2x minus 2y is equal to negative 10. And what I want to do is I want to add 8 to both sides. So I could do it like this. I could add 8 to both sides. But remember, our system is saying that both of these statements are true. That 2x plus y is equal to 8 and negative 2x minus 2y is equal to negative 10. So instead of adding explicitly 8 to both sides, I could add something that's equivalent to 8 to both sides. And I know something that is equivalent to 8 based on this first equation. I could add 8, and I could do 8 on the left-hand side, or I could just add 2x plus y. So 2x plus y. Now, I really want you might want to pause your video and say, okay, how can I do this? Why is Sal saying that I'm adding the same thing to both sides? Because remember, when we're taking a system, we're assuming that both of these need to be true. An xy pair satisfies one equation if and only if it satisfies the other. So here we know that 2x plus y needs to be equal to 8. So if I'm adding 2x plus y to the left and I'm adding 8 to the right, I'm really just adding 8 to both sides, which is equivalence preserving. And when you do that, you get these negative 2x and 2x cancels out. You get negative y is equal to negative 2. And so I can rewrite that second equation as negative y is equal to negative 2. And I know what you're thinking. You're like, wait, when I'm used to solving systems of equations, I'm used to just adding these two together, and then I just have this one equation. And really, that's not super mathematically rigorous, because the other equation is still there. It's still a constraint. Oftentimes you solve for one, and then you, quote, substitute back in. But really, both equations are there the whole time. You're just rewriting them in equivalent ways. So once again, this system, and this system are all equivalent. Any xy pair that satisfies one will satisfy all of them, and vice versa. And once again, we can continue to rewrite this in equivalent ways. That second equation, I could multiply both sides by negative 1. That's equivalence preserving. And if I did that, then I haven't changed my top equation. 2x plus y is equal to 8. And on the second one, if I multiply both sides by negative 1, I get y is equal to 2. Once again, these are all equivalent systems. I know I sound very repetitive in this. But now I can do another thing to make this, to keep the equivalence, but get a clearer idea of what that xy pair is. If we know that y is equal to 2, and we know that that's true in both equations, remember it is an and here. We're assuming there's some xy pair that satisfies both. 2x plus y needs to be equal to 8, and y is equal to 2. Well, that means up here where we see a y, we can write an equivalent system where instead of writing a y there, we can write a 2, because we know that y is equal to 2. And so we can rewrite that top equation by substituting a 2 for y. So we could rewrite that as 2x plus 2 is equal to 8, and y is equal to 2. So this is an and right over there. It's implicitly there. And of course, we can keep going from there. I'll scroll down a little bit. I could write another equivalent system to this by doing equivalence preserving operations on that top equation. What if I subtracted 2 from both sides of that top equation? It's still going to be an equivalent equation. And so I could rewrite it as, if I subtract 2 from both sides, I'm going to get 2x is equal to 6. And then that second equation hasn't changed. Y is equal to 2. So there's some xy pair that if it satisfies one, it satisfies the other, and vice versa. This system is equivalent to every system that I've written so far in this chain of operations, so to speak. And then, of course, this top equation, an equivalence preserving operation is to divide both sides by the same non-zero value. And in this case, I could divide both sides by 2. And then I would get, if I divide the top by 2, I would get x equals 3 and y is equal to 2. And once again, this is a different way of thinking about it. All I'm doing is rewriting the same system in an equivalent way that just gets us a little bit clearer as to what that xy pair actually is. In the past, you might have just assumed that you can add both sides of an equation or do this type of elimination or do some substitution to just, quote, figure out the x and y's. But really, you're rewriting the system. You're rewriting the constraints of the system in equivalent ways to make it more explicit what that xy pair is that satisfies both.
That was confusing. How we get there? So to get to 5, we just, and to get to 3 plus 12y. To get to -1, we did uh, x 12 -9. So this one we did x 12 How? Explain, please. Oh, you just bad. Nope. Added. So it's negative 9x. Y. So just Leo. X minus 7y. I don't get this. These are the same. Replace one equation with itself. I don't know. What the fuck is the answer? Swap the order of equation. Oh, stupid. Yeah, just the order. this one they just, so in order to get x plus 4, yep, plus 4. I don't understand the meaning. Subtracted. No. You added. Negative x, negative 5y, 5. There's elimination. Oh. My head hurts from. I've only been live for 3 hours and 23 minutes, but I was studying. Started around like 11:30, 12.
After you cross the Troll's Bridge and you save the prince or princess, you return them back to their father, the king, and he's so excited that you returned their son or daughter to him that he wants to throw a brunch in your honor. But he has a little bit of a conundrum in throwing the brunch. He wants to figure out how many cupcakes should he order. He doesn't want to waste any, but he wants to make sure that everyone has enough to eat. And you say, well, what's the problem here? And he says, well, I know adults eat a different number of cupcakes than children eat. And I know that in my kingdom, an adult will always eat the same amount, and a child will always eat the same amount. And so you say, King, well, what information can you give me? I might be able to help you out a little bit. You're feeling very confident after this troll situation. And he says, well, I know at the last party we had 500 adults, and we had 200 children. 200 children. And combined, Combined, they ate 2,900 cupcakes. 2,900 cupcakes. And you say, okay, that's interesting, but I think I'll need a little bit more information. Have you thrown parties before that? And the king says, of course I have. I like to throw parties. Well, what happened at the party before that? And he says, well, there we also had 500 adults. 500 adults. And we had 300 children. 300 children. And you say, well, how many cupcakes were eaten at that party? He says, well, we know it was 3,100 cupcakes. And so you get a tingling feeling that a little bit of algebra might apply over here. And you say, well, let me see. What do we need to figure out? We need to figure out the number of cupcakes on average that an adult will eat. So number of cupcakes, but for an adult. And we also need to figure out the number of cupcakes for a child. So these are the two things. These are the two things that we need to figure out, because then we can know how many adults and children are coming to the next brunch that are being held in your honor and get the exact right number of cupcakes. So those are the things you're trying to figure out, and we don't know what those things are. Let's define some variables that represent those things. So let's do A for adults. Let's let A equal the number of cupcakes that on average each adult eats. And let's do C for children. So C is the number of cupcakes for a child on average. So given that information, let's see how we can represent what the king has told us algebraically. So let's think about this orange information first. How could we represent this algebraically? Well, let's think about how many cupcakes the adults ate at that party. You had 500 adults, and on average, each of them ate exactly A cupcakes. So the total number of cupcakes that the adults ate were 500 times A. How many did the children eat? Well, same logic. You had 200 children, and they each ate C cupcakes. So 200 times C is the total number of cupcakes that the children ate. Well, how much did they eat in total? Well, it's the total number that the adults ate plus the total number that the children ate, which is 2,900 cupcakes. 2,900. So let's do that. Apply that same logic to the blue party right over here, this blue information. How can we represent this algebraically? Well, once again, how many total cupcakes did the adults eat? Well, you had 500 adults, and they each ate A cupcakes, which is an unknown right now. And then what about the children? Where you had 300 children, and they each ate C cupcakes. And so if you add up all the cupcakes that the adults ate plus all the cupcakes that the children ate, you get to 3,100 cupcakes. So this is starting to look interesting. I have two equations. I have a system of two equations with two unknowns. And you know from your experience with the troll that you should be able to solve this. You could solve it graphically like you did in the past, but now you feel that there could be another tool in your toolkit, which is really just an application of the algebra that you already know. So think a little bit about how you might do this. So let's rewrite this first equation right over here. So we have 500A plus 200C is equal to 2,900 cupcakes. Now, it would be good if we could get rid of this 500A somehow. Well, you might say, well, let me just subtract 500A. So you might say, well, I just want to subtract 500A. But if you subtracted 500A from the left-hand side, you'd also have to subtract 500A from the right-hand side. And so the A wouldn't just disappear, it would just end up on the right-hand side. And you'd still have one equation with two unknowns, which isn't too helpful. But you see something interesting. You're like, well, this is a 500A here. What if I subtracted a 500A and this 300C? So if I subtracted the 500A and the 300C from the left-hand side. And you're like, well, why is that useful? You're going to have to do the same thing on the right-hand side, and then you're going to have an A and a C on the right hand. And you just say, hold on 1 second here. Hold on, I guess you're talking to yourself. Hold on 1 second. I'm subtracting the left-hand side of this equation, but this left-hand side is the exact same thing as this right-hand side. So here I could subtract 500A and 300C, and I could do 500A and subtract 300C over here. But we know that subtracting 500A and 300C, that's the exact same thing as subtracting 3,100. 500, let me make it clear. This is 500A minus 300C is the exact same thing as subtracting 500A plus 300C. And we know that 500A plus 300C is exactly 3,100. This is 3100. This is what the second information gave us. So instead of subtracting 500a minus 300c, we can just subtract 3100. So let me do that. This is exciting. So let me clear that out. So let's clear that out. And so here, instead of doing this, I can subtract the exact same value, which we know is 3100. Subtract 3100. So look at it this way. It looks like we're subtracting this bottom equation from the top equation, but we're really just subtracting the same thing from both sides. This is just very basic algebra here. But if we do that, let's see what happens. So on the left-hand side, 500a minus 500a, those cancel out. 200c minus 300c, that gives us negative 100c. And on the right-hand side, 2900 minus 3100 is negative 200. Well, now we have one equation with one unknown, and we know how to solve this. We can divide both sides by negative 100. Divide both sides by negative 100. These cancel out. And then over here, you end up with a positive 2. So C is equal to positive 2. So we've solved one of the unknowns. Each child, on average, drinks 2 cups. So C is equal to 2. So how can we figure out what A is? Well, now we can take this information and go back into either one of these and figure out what A has to be. So let's go back into the orange one right over here and figure out what A has to be. So we had 500A plus 200C, but we know what C is. C is 2. So 200 times 2 is equal to 2900. Is equal to 2900. And now we just have to solve for A, one equation with one unknown. So we have 500A, 200 times 2 is 400, plus 400 is equal to 2900. We can subtract 400 from both sides of this equation. Let me do that. Subtracting 400. And we are left with, this cancels out. And on the left-hand side, we have 500A. This is very exciting. We're in the home stretch. On the right-hand side, you have 25, 2500. 500A equals 2500. We can divide both sides by 500. And we are left with 2500 divided by 500 is just 5. So you have A is equal to 5, and you're done. You have solved the king's conundrum. Each child on average drinks 2 cups of water, sorry, not cups of water. I don't know where I got that from. Each child eats 2 cupcakes, and each adult will eat 5 cupcakes. A is equal to 5. And so based on how many adults and children are coming to the brunch in your honor, you now know exactly the number of cupcakes that the king needs to order.
Whew. I am done for today. I'm tired.